My name is Rodrigo de la Peña Gutiérrez. I work for Kyocera AVX, and I have the position of technical sales for the RF and antenna components of the division. However, my background is an antenna engineer. Just for instance, for the people that is not used to Kyocera AVX, it's a really big company with a really big catalog. So the typical components that we propose is capacitors, antennas, RF microwave, sensors. We do also connectors, different type of crystals, of SAW filters, and also the circuit protection, and many more. I'm gonna be focused really in the RF and antenna related, since I'm serving this department. It's a really big company, as mentioned. It's a 3 billion company, 3 billion euros company, more than 20,000 employees, and different factories spread in different sites in offices in the globe. So, what is LDS? Basically, it's a manufacturing process that can allow you to metallize some, to create some traces of metallization over plastic. So you need a specific plastic that has specific adhesives. LDS is the acronym of laser direct structuring. So basically it's because we use a laser to activate this process. You need an injected molded plastic in order to make it work. There is some different materials or different methods that can be used for prototyping, but is not something that is reliable for mass production. How it works. So there is different steps, but we can try to resume this in 4 big steps. So basically, you have a specific resin that we have properties shared with the resin you used to normally, like ABS, PC, these kind of plastics, but it's specific for LDS with the specific additives. After that, you will have a preload laser machine that will burn or that will draw the pattern that you would like to metallize. After that, you will, the next steps is to have this preload shape in the machine, and after you will burn it. That is the third step. And after that, you go for a metallization bath. So it can be different type of components. Typical for antennas for air application is copper nickel. After you can have also some plating in silver and gold as well. This shows the typical stages of the part. This is an example of a main antenna for a smartphone. So as you can see, in the first stage is only the plastic that is molded. You have some speaker that is over molded there. You have some screw holes. The second stage is when you have the laser going through the plastic. So as you can see, that you already see the traces, but it's just born. So it's activating the additive that is in this plastic part. And after you have the metallization, depending the type of finishing that you are looking for. So those are the major steps. Of course, you can add some stages, like some cosmetic definition. Some products, they have the antennas or the metallization outside the box, so you can have different type of finishing for moisture, for a cosmetic purpose, even for some kind of painture to make it more discreet or to make the plastic look like a metal. For example, some phones have some inserts that make it look like a metal phone, but it's plastic in the end for the areas for these RF parts, right? Well, this is a QR code. If you want to see some videos from the factory, that's how the machine is running. Also, that you need something that you need to take in consideration is that it's not only, if talking from the example of an antenna design, it's not only the design of your traces that need to be considered, it's also the plastic part. So you need to think about the mechanics. So let's say the final product has a specific specification regarding the strain activeness, if it's for RF or maybe it's just for connection, if it's for high temperature. For example, we have some standard parts that can go through SMD process, so really going high in temperature for the soldering period. So we need a specific high temperature resistant plastic. If not, it will melt. Of course, you have the coloring properties. If it's some inside carrier or inside cap, it's not a real issue. But if you have something outside, you will need specific colors if you are aiming for aesthetics, for something aesthetic, right? The flame retardant, in case you need the application again, depends. You need some qualities of the plastic for this, and also the permittivity that is again related to the RF losses or the type of application. Some plastics are not really recommended for over 1 gigahertz, and some of them are specific for this. The price also varies depending the constraints. What are the benefits of using LDS process besides, for example, FPC process or metal stamped antennas? So basically, you will have total freedom of your shape. Let's say you have a carrier that is a little bit curved, that is also like a semi-sphere size. So as soon as this laser can hit to activate that part, it's going to be used for the antenna point of view. It's quite interesting where the size is quite limited. We don't really have a lot of room to draw the patterns for the antennas, so you can save space, but you can also optimize the performance. You can also use it to make some tracks. For example, you have some cables, and you would like to replace these cables by some LDS patterns, so you can have your plastic part, and the cables will be drawn, if we can call it like that, in the surface. This technology is not really suitable for high power, so something you need like a 10 watts, 20 watts is not suitable since the metallization is quite thin, so it will burn. Also for the integration density, we talk about the example of the smartphones. It can be some payment terminals, it can be laptops, these kind of things. The flexibilities we were already discussing. Performance optimization is part of the flexibility. Also, well, the economic and environmental application is more related to the production itself, because like that you will have a part that might be a screw, like the example we saw before. And so in the moment you screw or you attach this part in a more automated process, is something that's going to be cost effective for high volume application especially. This is an example. I mean, the idea is not to promote the products itself, but it's just to give you an example of what we can do with LDS. This is an SMD ultra-wide antenna, so it's quite small. It's like less than 1 centimeters height. It has some pads in the bottom, so it can be soldered SMD. That gives you the precision of the idea, what we can do. As you can see, the mechanic is important, because in this case, we have to think about some part for the pick and place. We have to think about some parts of how to build the mold, also to allow the injection and load those in the laser machine, and also use it in this way, right? This is a gold plated for the antenna purpose, for aesthetic purpose, so it's not a real big issue in that. Can be for the other frequencies, just to give you an idea of the frequencies of the size. Normally the constraints or the guidelines for this kind of application, you need tracks that can even a little bit less than a millimeter. So some tracks that is maybe 0.6, 0.8 width is something you can do. If you are not conducting high power or lines that can have a big coupling between them, it can be interesting. This is another example. This is much more bigger design. This is a helix antenna. The helix antenna commonly, they are like FPC, so they are a little bit troublesome to mount in the PCBs. So those are SMD product, like that the customer has total freedom to put in the design. And again, so you have 4 fits for this antenna. We don't see it, but in the bottom we have the fits, and we also have in the corners some mechanical attachment, mechanical pads that can help to support this, because it's a little bit big antenna, is something like 28 by the 30 size. Something that you need to take in consideration while designing an LDS part is the total shape or the total size, because you will need to use this specific resin that has a higher cost than the typical resins in plastics. So that means that if you are using only a small fraction of the surface of your part for the laser, you will have to inject a big portion of plastic for this. So that's why some carriers or some parts that can be add on of the design can save the cost or improve the design from this point of view. Other examples that are more like dense applications are those. In the bottom, you will have 3 examples for mobile phones. This is basically LTE antennas. This is a GPS antenna for a smartwatch. As I mentioned, you have just a small add-on that is inside of the smartwatch. Once you close the smartwatch, you ensure the contact, so you're improving a small part to do the antenna. we can do that in the full part of plastic of the smartwatch, but it's going to be a huge part compared to that. So production cost is going to be higher than that. Is to optimize. This is an example of a IoT device that you don't really have space for the antenna itself. It's a dog tracker, so you put it in the collar. So basically, it's like the metal for the dog. It's not this big. It's a little bit smaller. So something it was for T-Mobile in the US. So they were trying to aim for something more aesthetic. So at the end of the day, in the PCB, there is no room. So they have this inner layer, is not the outside layer. So, and like that, they have an LTE antenna and a GPS antenna, and they can work on that. And after, they just put a cover on it. The contact for this kind of antennas is also a challenge. It's something you need to take in consideration. You can have a cable soldered over there. You can have components soldered on the plastic, but it's also a cost and a complexity that you add. But let's say that you have some springs or some pogo pins or even some gaskets, conductive gaskets in your PCBs. Once you add the part, if you can make your mechanic design in certain way that when you will close the lid, it will contact, it will be improved a lot, these kind of stages. Something I would like to add as well is that LDS is not only for RF applications, so it can be for a bunch of stuff as well. Like I mentioned, you can do some connections. Let's say in some designs, customers were not really interested in anything related to RF. Let's say I would like to remove some buttons, or I would like to remove some cables, like that. They improve this, and they have some parts that are removed in the design, and they are just replaced by the plastic part. One of them is this MRI fixture. So used to be a lot of wires and a lot of small metal parts like clamps and guiding these kind of wires. So everything was replaced by LDS tracks. It's still metal because you have an additive, you have a metallization, but the amount of metal has been greatly reduced. Improving the application for this high magnetics environment is something that can be also do for medical, for example, for wearables. So it's something that it can be think not only from the RF perspective. Of course, the plastic can be even simple because you will need low losses for RF plastic, or it can be like an hybrid design. For example, sometimes we have an antennas and say, okay, I would like an NFC coil draw in it. I would like to have a capacitive sensor on it. So we can also do this kind of implementation as soon as there is room in the plastic, as soon as the plastic is for LDS application, we can have that. So it's something that is really advantageous when you want a high density integration, or when you want to put several metal elements in the same part. Sometimes say, okay, I have a PCB antenna, like quite a standard antenna, I will replace it with a plastic. It's not going to be cost effective. In this case, you really need to have this requirement. So like that can be really from an integration point of view or from cost saving point of view, interesting for your design. This is one of the last slides that I have for you. Basically, this shows you the steps we do at Kyocera AVX when you go for a custom antenna from the scratch to the final product. Of course, this is taking in consideration that you are doing an LDS antenna. For instance, it's an example of what we can do if you require something complex as a smartphone, for example. So basically what we do is we review your design, we do forward some feasibility studies. The first test we do is not with LDS itself, it's with something that just with copper or similar to FPC application, because at the end, from the performance point of view, it's going to be quite close to that. And as I mentioned, from the manufacturer point of view, prototyping LDS can be quite a challenge. I know there is some paints that you can have some 3D model, 3D printed model, and you add some special painture that you can metallize. For other applications can be fine. For RF, sometimes depending on frequency, it can be quite tricky. So we try to avoid that in terms of precision. After that, well, we have the proof of concept. We have to align mechanical, RF, or you want some wires or other electrical designs at the same time. Once everything is done, we go for some test optimization. Also, we can do the tuning and whatever is related to the antenna or the design itself. After we can validate with some building samples. So you need to take in consideration also the molding fees, because when you design this kind of part, you will need to do this. In the case you already produce or you already buy your casing, well, basically it's the same mold. Is one of the advantages also for LDS compared to the two shots metallization is that the same mold that you use for the plastic, the typical plastic case, it can be used for LDS application just with the proper resin. After that, of course, we do the final test, we do the parts, we test it. Everything that is related to RF is tested 100% for this kind of antennas or application. Of course, we have to do some builds for the jigs and stuff like that for qualification, and it's something we are doing in that. Regarding the design and implementation from us, everything related to design itself is done in Europe. So the R&D in charge of LDS is the same department as antenna. It's in South France. Regarding production, Kyocera AVX has factories for LDS in Korea, because one of our biggest customer is placed over there doing smartphones, and also we have factories in China and Vietnam as well. Those are big quantities production lanes. Again, for example, the example I showed with this dog metal, it can be also, it was a small volume, we can do that as well, but they assume that the cost of the part is going to be diluted in small quantities, so it was a premium product for them, so we managed to get some agreement on it. Also, well, that's almost the end. I'm just to compare a bit with FPC and LDS. LDS, again, if you have that, like a high density, high volume application is ideal. Also when you have weird shapes, like the metal, for example. But if you have something like flat, and you can assume some sticker on it like FPC, FPC can be also the same approach from the antenna point of view or the metallization point of view. Less reliable because it might move, because it's still a manual activity, but can be some trade-off for small volumes or for simple architectures. I think it's everything. I don't know if you have any questions. I have some examples that I can share with you if you would like to see. That's what can be do from the antenna point of view. As you can see, we can do several stuff. For example, one of that parts has bias. You can also implement some bias. I think I have it in one of the pictures. I don't really see it properly, but you can do some bias in having the pads, connection pads in one phase, and you can have the rest in the other phase. So this is a clear code for a white paper we have about LDS technology. It's something is available also for other suppliers. In the last slide, I have a code. If you want to have your CPD credits. And if you have any questions regarding the product, the implementation, or whatever limitation, don't hesitate. Also, I would like to highlight as well from the process itself is that this technology doesn't really tolerate the 90 degrees shapes if you are using different phases of the plastic. So it's better to have a minimum of 0.3 millimeters radius to avoid any kind of miscontact or ruptures in the contact. Anyway, it's checked in the factory, but like that, if the design is strong enough, we will improve the quality yield at the end.